I don't know, which is like 13 to 90. It's like, yeah, it's I spend any of this like, yeah.
What I'm doing now is actually finding some tables. This is an online version of your book. And I'm trying to... Okay, there you go. Okay, what is the full screen here? There it is, full screen. Oh, zoom in. There's no at the top here.
Where it says page fit, underneath the bar where you enter the website.
Left.
Left.
Here.
Get to the left of that. Plus sign.
Ah, plus.
Plus sign.
Here. Oh, okay. Okay. Yes, today we're gonna continue. It will be slightly more difficult to record everything that is relevant today because I don't know for people who are online how well they would be able to see what is on the screen here. But what is on the screen is a table summarizing some of the stuff that we covered last time during the lecture, and that's the mathematical relationship between a future value of investment or a loan or any time market transaction and the present value, coded or regulated by interest rate and by the duration of the investment or maturity. You will remember these equations. This one equation in two forms. Where F is the future amount of money, P is the present money, and this is the so-called compounding factor or a discounting factor, depending how you solve the equation. And we've seen that the present value is defined as a future value given times 1 plus R. And one of the conclusions that we derived last time about the present value and future value was that there is a correspondence or a direct proportionate relationship between the future value or future payment in a time market transaction and the interest rate. And there is also positive correlation between the future payment and the time duration of the transaction, which means that the longer time period over which a time market transaction is carried out, higher the future value of investment will be, higher the future payment will be. And the same thing applies to the interest rate. Higher the interest rate, higher the compounded value of investment will be. So here you have a table that shows some, how is that the case, how that could be the case. It's very simple. You can see mathematically here that has to be the case, because for when you look at the basic equation here, you see that f is greater than p. Why? Because 1 plus r is greater than 1. When you multiply any positive number, let's say p, by a number greater than 1, you get a bigger number. So then higher, and 1 plus r is controlled by r. R has to be a positive number always, because interest rate is a positive number. So 1 plus r is greater than the larger the entire compounding factor of 1 plus r is. So then you can say that larger the f, larger the r, higher the f, higher the future payment. So this is what you see here. Let's say, take any time duration, let's say 1 year. So $1 at the present, exchanged as a loan, for example, will be worth with the 3% interest rate for $1.03 after 1 year. At 4% interest rate, it's 1.04. At 5%, 1.05, and so on down the line. So that's what is seen in all these horizontal lines and all these rows. 5 years, it's larger, and then it increases with an increase in the interest rate. So that's one thing. The second thing is that compounded value of present $1 will increase also with a variation in the time period over which a transaction is taking place. So even with the same interest rate, a 6-year loan will yield you larger additional amount of money than a 3-year. Remember the equation that covers that. T equals P times 1 plus R to the power of T. That means for a time period of 2 years, if you say that T is equals 2, then the compounded value, F, future amount of money, will be the present money $1 forever times 1 plus R squared. So this number will be bigger, F2 will be bigger than F1. Why? Because 1 plus R squared is bigger than 1 plus R. Okay. Why is 1 plus R squared bigger than 1 plus R? Because a positive number greater than 1 squared will give you a bigger number. It's basic math. 1 plus R to the power of 3 will be bigger than 1 plus R squared. And so on down the line. So that's the reason that, again, the future compounded value will vary with the change in the time period over which a time market transaction is taking place. So that's what you see in those vertical columns here. Let's say with 4%, if you get your money in 1 year, you will get 1.4, but if you get money after 10 years, you're going to get 1.48 because of this effect of compound. You're going to be multiplying 1.4 10 times. You're going to get a larger number. So that's the basic fact. So this table shows you just in a graphical fashion what you can calculate mathematically without a table. Is here you have $1 for the simplicity, say $1 of present money, and then you have a table showing you what kind of combinations, depending on the interest rate and the time duration of the transaction, the time period in question, how much money you will get eventually. What is the future value of that present $1? So in 10 years, with interest rate of 4% is 1.48. So what is the best of both worlds? When you get most money, what kind of transaction is? will yield the highest possible future value of present $1. So if you invest for 50 years, an interest rate of 20%. So after 50 years, you're going to get $9,100. If you receive your payment in one lump sum after 50 years. So imagine that you're investing now, you're all young, 20 years old, in 50 years you're going to be 70, retiring. So you can get $9,100 if you can make it to save for 50 years at an annual rate of 20%. That's unlikely, but that would be the future amount that you have to pay. So that's the first demonstration. The first table that kind of illustrates the values of future payments as a function of interest rates and time duration. And say that the future amount is a positive function of both. It varies in sync with them. It moves in the same direction. The longer the time period, higher the compounded value, or future value, higher the interest rate, higher the compounded value. But for our purposes, it is even more interesting to take a look at the second table here. This is all chapter 30, the previous chapter. I told you that I was not going to bother you with the tables last time. This also illustrates the same thing here. You have $1, and then you have a variation in the value of the investment over time. This is the lowest interest rate. This is higher interest rate. So you see, as time goes by, the increment in value is highest with the highest interest rate. That's just another graphical representation of the same thing. But that's not what I wanted to spend more time on. The next table is important for us. Here. This one. This one shows you the present value of future $1. Remember, what is the present value? And anyone remind us? What is the present value? What is that? The value of what at the present moment? No, the value of future money, the value of future gain, or value of future money for which, or claim, secure claim on future money today. So $1 in 1 year, or the present value of future $1 at any one given point in 1 year, or 2 years, 3 years, 4 years. How much would you pay for that $1 right now? That's the present value. This is the formula that calculates the present value. Now, what we concluded about the functional relationship between the present value and interest rates and time period. In the case of the future value, there is a positive correlation. It's a positive function. It varies in the same direction with them. Here, it's a negative function, which means that the present value decreases as the interest rate goes up. Again, we can prove that mathematically. Here, it's the same thing. This discounting factor reduces f because it's a number bigger than 1. When you divide any positive number by a number bigger than 1, you reduce it. Larger they are, larger the discounting effect will be. So the same thing just that we did for the future value, applied just the present value. So higher the interest rate, lower the present value, and vice versa. But also the time period. Longer the time period, lower the present value. So what does that mean? Intuitively, that means that if you're getting $1 of future money is in a more distant future, you will pay for the claim to that dollar right now less than if it's for 1 year. If it's for 5 years, that's worth right now to you less than if it's in 1 year. It's later, the time preference. So you see here, for example, for 2 years, it's f over 1 plus r squared. So 1 plus r squared is bigger than 1 plus r. So that means that the reduction of f for a period of 2 years will be higher. So then P2 is smaller than P1. P1 will be f divided by 1 plus r. P3 would be f divided by 1 plus r to the power of 3. So P3 will be smaller than P2. Okay, so present value of a future good or future money, whatever you want, is a negative function of both interest rate and the time period. But you see that in this table here. You see with an increase in interest rate, the present value declines. You're at for $1 in 1 year, after 1 year period, at an interest rate of 3%, you're ready to pay 97 cents right now for a secure claim of $1 in 1 year. At 7% interest rate, you will pay only 94 cents. 12%, it's only 89 cents. This is Greek government bond. This is German government bond. Remember the example why German government can afford more money, get more cash from creditors, because the interest rate of German government bonds is very low, because it's a very secure investment. That means that the present value of a government bond, the present value of a future claim on German government's money is higher than the equivalent claim on the Greek government bonds. When the German government says, I'm going to pay you $1 or €1 in 1 year, that's far more secure than the Greek government. So then the investors can't build that into the interest rates. That's the reason why I pay more money right now to the German government. What about the time period? You see that, let's say, at 5% interest rate, 95 cents will be the amount of money paid right now. But for 10-year period, it's only 61 cents. If you're getting $1, it's removed 10 years, you're going to pay far less for that than if you get money in 1 year, 2 years. Okay, what these two examples have in common is that they treat the time market transactions as a one-time events. I give you the money, you return the money back in one payment, irrespective of when it happens. Both the first table and the second table treat the time market transactions as one-time transactions. And those calculations apply only to one-to-one transactions. Now, the problem with this, and now we're moving to the next chapter, 31, is that not all time market transactions are such. Many of them are different. Many of them are structured as a series of future payments. Let's say annual payments. So whenever you are buying machinery or hiring workers or deciding to save money for the retirement, you're not necessarily interested how much money you will get in one lump sum payment right now, or how much money you will need to pay right now at this moment. But you're thinking about how much money you will need to pay over a certain period of time every year, or how much money you will receive over a certain period of time year after year. Now we need some formula, we need some mathematical framework how to think and how to calculate, how to think about and how to calculate then the present and future values within this context. Payments that repeat time and again. And the easiest way of thinking about that is to talk about annual payments, or so-called annuities. In that particular case, what would we like to do is to calculate the present value. For example, we can start with the present value. Not of a one future payment in future money, in 1 year or 3 years, 5 years, but to calculate the present value of a series of future or a stream of future payments over a certain period of time. Let's say that you want to buy a right to a stream of payments, 10 years of payments, 4 years of payments, $1 each annual. 4 annual payments, you can buy that package. How much money you would need to pay right now to receive a right? To that kind of payment. The present value of a future stream of payments. So now how would you calculate that? Any ideas? What is the present value of a stream of payments? So you want to receive $1, let's say $1, let's say that the interest rate is 5%. And then you want to receive, you want to calculate how much money you need to pay right now to get 4 equal annual payments, $1 each in the next 4 years. Can anyone try to calculate this? It's a very good chance to get extremely good participation rate. Can pull this one off. When you look at it, it's easy, but it may be kind of overwhelming and complicated to look at all those numbers and all things. But think about it for a moment. So you want to buy a right to receive a payment of $1 in year 1 and a payment of $1 in year 2.
You have to find the value of each of those years and like back it up to current.
So how do you find the value of each one of these? What is the present value of the first year payment? What is the formula for that? How do you calculate that? Let's say here, 5%. It says it's 0.95. How did they get this number? That equation. So 3, future payment is, what is the future payment? 1 divided by 1.03. So that then you have a present value of the first year equals, say, F over 1 plus R. So what is the present value of the second year now? That's simple, straightforward. Squared.
F over 1 plus R squared?
Yeah, squared. Third year to the power of 3, fourth year to the power of 4. What is the final step here? What is then the present value of the entire series of payments?
You add them all together.
Add them up all together. So the present value, let's say big, B equals B1 plus B2 plus B3 plus this big capital letter P is the present value of a future stream of 4 payments, each $1 each. So what would be that at 5% interest rate? 1.86, it will be less. Somebody can calculate this. So it will be obviously less than 4. It will be 3 point something. So see, obviously then nobody, so now show this to our audience here, our online audience. So these are the equations. Hopefully people who are watching the video can disentangle that. On this table here, people online, you now can open up your book on page 483 in order to follow what I'm going to be talking about now, and look at the table 30.2. So the table tells you that in a very long period of time, with a very high interest rate, the present value of future good goes almost to 0. Nobody would pay much for a secure claim to $1 of future income in 50 years at 20% interest rate. On the other hand, a short-term loan or a short-term time market transaction at low interest rate, very high present value, which is approaching 100% of future value. So it's the exact opposite of the future value that we discovered. Further into the future, and when you increase the interest rate, you increase the future value, increase the future compounded value. So now we can move to the next chapter here. Again, where we have an explicit table, chapter 31. It does all the calculation that we did. Now, just summed up. Now you're going to see how that what it looks like. So you don't need to do in a kind of pedestrian way all of these calculations. They give it to you here. So remember what was here, 5% is 0.95. So people who are online, take a look at chapter 31, table on page 492. So at 5% interest rate is 0.95. Then for a 2-year, for a stream of 2 future payments of $1 each, the present value is 186. That's 0.95 plus 0.91. That's the value for the second year. You add them up all together, you get this cumulative present value for $2. For $3, divided into 3 equal payments of $1 each, you get to 2.72, and so on down the line. So what can we tell about the relationship now between the interest rate and time duration and present value of a future stream of payments? How they change. So stream of future payments reduces with an increase in interest rate, but it increases with the time duration. Any questions, last one? You get the relationship between this table and the previous one? Okay, any questions about that? So here they just did the mathematical calculations for arithmetical calculations for us. We don't need to add them up, they did it for us. These are the same numbers from the previous table, just translated into the present values of a series of future payments instead of discrete future payments for every time period, individual payments. So what could be the applications of this? Why would anyone want to calculate these present values of future streams of payments? any kind of a discounting process that involves an ongoing operation, like buying a machine that you want to use over a period of time, like 5 years. Let's say that 5 years is what is called the working age. No, working age is amortization period over which a machine can be used. What is the technical term for that? This period over which the machine is used. Forgot.
Depreciation or
Yeah, depreciation is a process that is ongoing, but what is the period over which a machine is usable? Working time or working age? Utilization.
Useful life?
Yeah, useful life. Yeah. So the period over which you can use it. So then, what do you want to do? You want to calculate. You want to calculate the how much you receive from a machine over. You want to buy a machine right now. You need to pay in cash right now. You then want to calculate how much you will receive in this future. What are the future earnings of a machine over a given period of time? And then depending on the interest rate, you will decide if it's too expensive for you, if, for example, interest rate is 4%, then you have to pay, let's say that the machine is $4,000 in cash. Now, you have to pay $4,000 in cash. And the machine can give you, if utilized over this period of time, can give you in first year, whatever, 1,200, in second year a little bit less. That adds up to, let's say, 4,100. Net earnings of this machine over a period of 4 years. Then you calculate, then you discount this by interest rate, and you see then if the present value, what is the present value of $4,100 of future earnings in 4 annual increments. And if it's less than $4,000, you don't buy a machine. The same for labor, discounting process of labor. So it happens in this way by calculating the present value of a future stream of payments that you can receive, future stream of income, future income stream that you can receive. How much money you will receive by employing somebody over a period of 4 years. Okay, one more thing here. There is an appendix here. There is a fourth table, which is just a variation on the first one. Give me just a second. This one. So what is this? Any ideas?
That's the payments at the end of the year with interest, or?
Yeah. So you don't pay your debt in one lump sum payment, but you pay it in equal installments. So what is then the future value of those installments at the end of each year? So again, the calculation here is simple. At the end of year 1, let's say with the 2%, interest rate. What would it be? Interest rate is 2%. So if you pay everything in 1 year, in one payment, you pay 1.20. If you pay in 2 installments, let's say, if you need to pay $2 worth of debt in 2 installments, what do you have then? Let us go back in order to better see this. Let us go back to table number 1. This is present value. No. Where's the compound? Let's check 31. Check 3. Yeah, compounded value. So see, this is from a standpoint of a saver, how much money you get. But the same is from a standpoint of credit or a lender. So for 2 years you get 1.06. For 3 years you get 1.09, and so on down the line. So now, if you want to apply the same calculation that we did for the present value, the series of future payments to retire debt, for example, what would be the calculation then? What would be the value for in year 1, let's say at 5% interest rate?
P plus 1/10.
Yeah. P1 plus R, so the first payment will be 10.5. What is then the value for the second year?
1 plus R squared.
Yeah. So you will have to pay then $2.25. No, $2.15. And so on down the way. One more thing. How much time do we have left? 9 minutes. Just one more thing before we adjourn. I think that I promised to clarify something for you last time. We have 10 minutes. Maybe I will have time right now. That by using the concept of present value, understanding the concept of present value, can help us understand the problem of the business cycle. You don't have that in your summary of the lectures. I will try to do a very brief version of that, like 10-minute version of the relationship between business cycle theory and interest rate and present value. I'll give you the dogma first. Dogma is that the recessions in business cycles, that means the periods in which the productivity and investment go down, are caused by the artificial decrease in interest rate. And by artificial decrease in interest interest rate, I mean the following. First, you need to understand what is the proper increase in interest rate. What causes the pure rate of interest to change? It's simple. It's a change in the composition of income. Saving plus consumption. So let's say that your income is $1,000. You save $100 and you spend $900. Your savings rate is 10%. What you do with your savings? You either invest yourself in your business, or you buy shares, stocks or bonds, buy stocks, or you put the money in a bank. In either case, actually, your money ends up in the private investment. These are different forms of investment. These two are financial intermediations. This is direct investment. So savings is translated, savings equals investment, directly or indirectly. What will determine the interest rate is actually the ratio between saving and consumption. Pure interest rate is determined by the time preference. How impatient people are. If people are relatively impatient about the future, the percentage of their total income that will be saved will be lower, and percentage of total income consumed or spent will be higher, and vice versa. If their time preference rate is higher, lower, that is they are less patient about the future, then they will be saving more and investing more and consuming relatively less of their income. Saving and investment is higher when the rate of time preference is lower, and people are less impatient, and vice versa. If people are more impatient, then the consumption at the present, greater proportion of their total income will be consumed and less will saved and invested. What changes the interest rate in this model? You can treat the interest rate as I'll draw the picture here. This is the interest rate, which is the price of money. Here is the quantity of money that you change hands in the loan transactions. It is determined by the supply and demand of loans. The equilibrium interest rate is at the intersection of supply of loans. That's this saving, how much money people save and are ready to lend to other people directly or indirectly. And the demand. Entrepreneurs that have demand for loans. This would be the equilibrium quantity of loans that will be created. This is the quantity of credit that will be created on the credit market. This is the interest rate at which this credit will be created. What changes the interest rate in a free economy, in a free market economy, is when this equation here changes, and the proportion between savings and investment changes. Let's say that people decide to save $200 instead of $100, and then consequently to spend on consumer goods only $800. Now the saving consumption ratio changes from 1 to 9 to 1 to 4. As a consequence of that, what happens here? The supply curve moves to the right. Supply of savings increases, credit increases, so the supply curve moves to the right. Simply $200 is greater than $100, greater supply of savings. As a consequence of that, the interest rate will go down, the new equilibrium interest rate will be lower, and the quantity of credit will be higher. That's a real decrease, a real drop in the interest rate, which is dictated by the changed time preference. So people are ready now to consume, to sacrifice more right now, to consume a little bit less in order to save and invest more for the future than in order to be able to consume more in a more distant future. Now, the problem is when central bank and private banks enter the picture and create credit out of thin air, create a mirage that there is more money and there is more credit than really is. The time preference hasn't changed, but the central bank printed money and created new credit that lowers the interest rate without a change in time preference of the people. The consequence of that is that buying consumer goods, consumption, spending will not go down while investment will go up because people will believe, deceived by this artificially low interest rate, that there is more savings than there really is. In the long run, what will happen? Take a look. Let this be a homework assignment for you. Take a look at those present value figures in chapter 30, table number 2, and tell me pertaining to the investments of different durations, different time periods. So we will continue with that on Friday. You will see that eventually the business cycle happens because artificially low interest rates encourage too much investment in the long-term business projects that are much more sensitive to the changes in interest rate. So when interest rate goes down from 5 to 3%, not all business projects are equally affected. All of them look a little bit more profitable than before, but the longer time period, greater the boost in investment is. We'll see. We will begin next class on Friday. Unfortunately, we couldn't finish it today. We will begin with this, with the final explanation of the relationship between the present value, between the concept of present value and the business cycle. Okay, maybe I shouldn't have began that because. Okay, any final questions here? Oh, okay. See you on Friday.
Would that mean since the interest rate's been like at 0 or whatever for a while? Like since the central bank?
That's a good question. They are now trying. What is at 0 now is not a real market interest rate. It's a rate at which the central bank gives to private banks.
But private banks are pretty low now anyways.
Yeah, they're low. You know what is the issue here? They get the money, they get cash, they get liquidity, but they don't lend it out. They increase their reserves. Yeah. That's what happened in the 2010-11. There was this quantitative easing, huge increase in money supply, but large parts of that money supply ended up in cash reserves because banks were cautious to create credit. So it's not enough. Sometimes the central bank can print as much money as they want. They will not create new credit that way because you need a cooperation of private banks. This process of recycling credit. I can, for example, one mechanism that I buy government bonds for private banks, financial institutions. I create cash out of thin air. That's how central banks create money.
So now there's been like a lot of.
And now people have new cash. They didn't have before. Now the question is, what are they going to do with that cash? The banks have cash. In the monetary ideal, people who advocate for an easy money policy, they believe that they're going to recycle that cash through the private banking system. So, for example, I buy from you government bonds to the tune of $1 million, or let's say $100. Then you lend that money to somebody. Somebody uses that money to buy from somebody else something, deposits 90% of that money in the bank, 10% has to be kept in reserves. Now you have $900 of new money. The second bank lends that money to somebody else. That person gets $900 of cash, buys something else from somebody else. $900 of new reserves end up in the third bank, 10% in reserves, $810 of new cash in the entire process of recycling. So eventually you end up with creating much more money than this initial purchase by the central bank. Now, in order for that to happen, you need a confidence in the financial system, and you need people to lend and borrow money. Banks to be confident that the loans will be repaid by people to whom they lend, and you need borrowers who are going to borrow. If you don't have that, then the quantity of credit will not increase very much.
And right now, it seems like there's a lot of people buying homes and whatnot, so there's a lot of people borrowing.
Yeah, now it seems that we are, in the last 4 or 5 years or so, it seems that the quantity of credit is increasing. So that's macro, if you remember. Did you take macro? Yeah, so remember this M2 aggregate. It includes the credit and savings accounts and so on. That's a good measure of how much this initial process of increasing the amount of cash in the economy resulted in an increase in the level of credit. So the idea of this credit eventually is that they overdo it. They have too much credit, too much money, too much investment, and eventually you cannot complete all of these projects, long-term and short-term ones. You create this speculative bubble. There is not enough real resources to cover all of that. So we'll talk about that on Friday.
I think we're not going to be here Friday either because we just picked up games this weekend.
All games,
in
okay.
Williston. So
Okay.
do you want to just like email you?
Yeah, just
Friday?
email me to
Remind you.
No problem.
Awesome. Thank you.
Good. See you.